In this video, we're going to look at an exception to the octet rule that often occurs with very large atoms. And by large atoms, I mean atoms that are in the third period or lower. Third period means the third row on the periodic table or lower. So these can occur with atoms in the third period or lower. So it is possible for me to build structures that have got more than 8 electrons around the central atom if the central atom is phosphorus, but not if it's nitrogen. Let's do an example like that. Let's suppose we want to do the Lewis structure for the molecule PCl5. Let's follow the rules that we've been following. Step 1, we need a skeleton structure. Okay, which atom should be in the center? I'll look at my periodic table. It looks to me like P is closer to the center of the table than Cl. So I will put P in the center of my structure. It doesn't matter how I arrange these Cl's around the P, as long as the P is in the center and the Cl's are on the outside. Second step, count the valence electrons. Well, let's see, what do I got? I got phosphorus, which is in the column with 5 valence electrons. And I've got 5 chlorines. The chlorines are in the column with 7 valence electrons. Okay, so 40. I've got 40 valence electrons. Step 3, connect the structure. You got to follow these steps in order or things just don't work for you. Okay, if I'm connecting the structure, what that means is draw a stick between the central atom and each of the outside ones. Now you can see something kind of strange happens there right away, because if each of these sticks stand for 2 electrons, I am going to have 10 electrons around that phosphorus. And that shouldn't be possible. It should want just 8. But if it's a very large atom, it can actually hold more than 8 electrons around it. So this is possible. I'm going to double check when something like that happens that I am in the third row or lower. This can never happen with the second row. You can never have what we call an expanded octet with anything that's in the second row. Okay, so I connected it. Well, how much did that cost me? 2, 4, 6, 8, 10 electrons. So if I subtract out 10 electrons, I've got 30 left. The next step is satisfy the outer atoms. That means the chlorines. Now, each chlorine wants an octet, wants 8, already has 2 from the bond that's in there. So each one wants 6 more. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Perfect, because I used up the last 30 electrons and I have none left now. So each of those outside chlorines is satisfied. Step 5, dump the remaining electrons on the central atom. Is the central atom satisfied? Well, Well, no, that's hard to answer here because we want the central atom to have an octet, and it's got 10. Is it satisfied with 10? If it's third row, third period or lower, and it has more than 8, it may be satisfied. Now that's not a very satisfying thing, maybe. So what we can do is go to the next step and assign the formal charges to see if this is actually a good structure. Alright, so remember how we assign formal charges. We take the number of valence electrons. The chlorine has got 7 valence electrons on the periodic table, minus the number of sticks and dots that are around it. Let's see, 1, 2, 3, 4, 5, 6, 7. We're not counting electrons, we're counting sticks and dots. So all of the chlorines are all the same, so they will all have a formal charge of 0. How about that phosphorus in there? Well, it's got 5 on the periodic table minus 1, 2, 3, 4, 5 sticks and dots. So it is a formal charge of 0. Now look, that's about as good as we can get. All of our formal charges are 0. So this is telling us this is a stable structure. In the next video, we're going to look at some more expanded octet molecules where you can choose to expand the octet in order to minimize formal charges.